Hello, welcome to this video in the internal combustion engine series. Today's lesson objective is to describe the four-stroke mechanical cycle for a reciprocating internal combustion engine. Let's begin by first making a quick taxonomy of internal combustion engine types. So if we start off with internal combustion engines, we can first classify them as either piston type or rotary type. Now, looking at the piston type, we can further classify them down as either spark ignition engines, which typically run off gas or petrol, or compression ignition engines, which typically run off of diesel. Looking at the rotary type, we can classify those as either Wankel, which run off gas or petrol, or gas turbines. Now, going back to the spark ignition engine classification at the top, those can further be broken down by the number of strokes it takes to complete a cycle. So either a four-stroke engine or a two-stroke. Same with compression ignition, either a four-stroke or a two-stroke. A Wankel engine by design is a four-stroke engine, and gas turbines don't have associated strokes, and so that classification is left blank. Now, everything you see here highlighted in green will be covered in this block of instruction for MC312. Anything in yellow will be covered in MC312, but in a later block when you discuss gas turbine engines and the Brayton cycle. And anything highlighted here in pink won't be covered in this course, but I want you to be aware that they do exist, and I encourage you to do some research on your own if you're interested in those topics. Now that we've seen that overview of the taxonomy of internal combustion engines, let's provide a little bit more detail. So first, we're going to talk about the classification by ignition method. First is the spark ignition engine. So in a spark ignition engine, you have a spark plug that takes electric energy and injects that via the spark plug into the piston cylinder, and it uses that energy to overcome the activation energy necessary to initiate this rapid chemical reaction we know as combustion of that fuel-air mixture. Conversely, if you have a compression ignition engine, the fuel is injected directly into the cylinder with compressed air. Now that compressed air, due to the compression, think ideal gas law, is at a high enough temperature that when the fuel is injected, it immediately vaporizes and ignites because the temperature is higher than the auto ignition temperature of that fuel. We can also classify reciprocating piston type engines by the number of strokes in a cycle. So let's introduce it and then we'll go into a little bit more detail in the next slide. So in a four-stroke, it takes four strokes to complete all functions of the piston. We'll talk about what those are in the next slide. Essentially, in a four-stroke engine, it takes 2 revolutions of the crankshaft to complete all the functions. And in a two-stroke engine, you have some functions combined into single strokes, so it requires 2 strokes to complete all the functions, and therefore only 1 revolution of the crankshaft. We're going to focus in this course primarily on four-stroke process internal combustion engines. So the first step is intake, the next is compression, next is expansion or power stroke, and the last is the exhaust stroke. And because it's a cycle, it will continue to repeat itself. Now, in a two-stroke engine, the intake and compression are combined into 1 stroke, and the expansion and the exhaust are in 1 stroke. But for a four-stroke engine, intake, compression, expansion, exhaust are all separate strokes. This figure from 13.3, or figure 13.3, I should say, from your textbook, depicts all 4 of these strokes. So the intake stroke, the intake valve opens, the movable piston moves from top dead center down to bottom dead center. On the compression stroke, the valves are closed and the piston moves up to compress that air. You have a spark if it's a spark ignition engine, or a fuel injector if it's a compression ignition engine, that now introduces either fuel or a spark into the piston cylinder, which causes the expansion due to the combustion process, which we could refer to as the expansion or the power stroke. And then lastly, we have to get rid of all those byproducts of combustion, and so you have exhaust, and it's going out the open exhaust valve. We talked about timing of that in a previous video. Now it's kind of hard to see on this static picture, so let's take a look at an animation, and let's build figure 13.3 and figure 13.4 from your textbook synchronously. So on my intake stroke, my intake valve opens and I have air or an air and fuel mixture enter my cylinder. And we see that plotted on figure 13.4, where I move from top dead center to bottom dead center, at which point the intake valve will close. Next, I have the compression stroke, and note at my compression stroke, I go from bottom dead center to top dead center. And just prior to reaching top dead center, I have the initiation of a spark, since this is a spark ignition engine I've depicted here, where I have heat into my system. The next stroke, we have the power stroke or expansion. So you see this rapid spike in pressure, and then you see the pressure start to drop off as the volume increases. Again, think ideal gas law, until we hit bottom dead center. It's through this power stroke where we get our net expansion work. So that's why it's sometimes called the expansion or the power stroke. Finally, the exhaust valve opens and the piston moves back up, exhausting all those byproducts of combustion, and the exhaust valve closes. Then the cycle repeats itself. Now you'll notice that there is a difference in the pressure from the exhaust to the intake, and we account for that difference due to pumping losses. This is what it looks like in a faster animated form. You say intake, compression, power, exhaust, and each one of your cylinders is going through this process. Let's take a look at what that looks like combined. So let's put it all together. Here we have an animation of a 4-stroke inline 4-cylinder engine where you have 4 pistons working in concert with one another, connected via the crankshaft. And that crankshaft is connected via the timing belt to the camshafts at the top, which are rotating to depress the springs on the intake valves and exhaust valves to keep everything synchronized. Now, as we noted in a previous video in the 4-cylinder engine, typically you have the first cylinder and the fourth cylinder in phase with one another, and the second and third pistons in phase with one another, but 180 degrees out of phase with pistons 1 and 4 for vibrational purposes. But I want you to also note that we've color-coded here intake, compression, expansion or power, and exhaust in the same color schema as you have in this animation. So there's always one piston that is producing power. And you can note that, for example, 1 and 4, while in phase motion-wise, are 180 degrees out of phase with regard to what stroke they're on. Intake, while one is on expansion, one on exhaust, while the other is on compression. And the same stands true for pistons 2 and 3. Let's talk about mean effective pressure. So first of all, what is mean effective pressure? Well, mean effective pressure is a hypothetical constant pressure that would have to be exerted on the piston during the power stroke to develop the same net work produced by the engine during one cycle. So why would we do that? Well, it provides a means to compare engines of different sizes. So let's take a look at figure 13.4. We'll recall that. And you know that the area in the curve is the work. I have a PV diagram, a pressure volume diagram, so the area inside the curve is the net expansion work. So if I wanted to compare engines to different sizes, that would be difficult because each would produce different net expansion work. But if I want to normalize that and compare it, I can use the mean effective pressure. So let's draw the same PV axes, except we're going to use specific volume in this case. And I'm going to have my specific volume top dead center, my specific volume bottom dead center. I'm going to draw some vertical lines coming up from that. And there is some hypothetical mean effective pressure when I go from the initial step of the process of the cycle to the final step. The area under that curve would represent the net work, in this case, the specific net work. In order to compute that, the mean effective pressure would be the net work divided by the difference between the volume at the bottom dead center and the volume at the top dead center. So the maximum volume divided by the minimum volume. Okay, you would agree that if I divided everything by mass, I could rewrite that as my specific network and my specific volumes at bottom dead center and top dead center. And knowing my relations previously between volume at bottom dead center and volume at top dead center, I could rewrite this as my specific network divided by my specific volume at bottom dead center times 1 minus the ratio of the volume top dead center to the volume bottom dead center. Well, this ratio should look familiar. It's 1 over the compression ratio. And this is equation 13.5 in your text. Okay, that wraps it up for the description of the 4-stroke mechanical cycle for a reciprocating internal combustion engine. If you have any questions, please contact your instructor. See you later.